Somewhere in the silent glow of the early universe, a shadow lingers, an enormous patch of sky, colder than the rest of creation. It stretches across billions of light years, defying every known law of cosmic evolution. Whatever shaped it left an imprint we still struggle to understand, a silent reminder that somewhere out there, the universe holds a cold secret it was never meant to have. This is the strange, cold spot in the universe that shouldn't exist. The impossible cold spot. High above the plane of the Milky Way, where the ancient light of the universe glows faintly in microwaves, lies a region that quietly breaks the rules. Astronomers call it the cold spot, a patch of the cosmic microwave background that is colder than it should be, a soft bruise on the first light ever released. The cosmic background itself is the afterglow of the Big Bang, formed when the universe was just 380,000 years old. And it is almost perfectly uniform, yet within that uniformity sits this single, puzzling imperfection, stretching across hundreds of millions of light years and colder by a few hundred microkelvins. The cold spot was discovered in 2001 by NASA's Wilkinson Microwave Anisotropy Probe, which mapped the temperature variations across the sky. Most of those variations were expected tiny fluctuations that would one day grow into galaxies. But within the data was something far larger, a circular blotch, about 5 degrees wide, colder than theory allowed. When the European Space Agency's Planck satellite later produced higher resolution maps in 2013, the feature remained. It was no artifact of noise or faulty sensors. Whatever caused it, it was real and enormous. The temperature difference may sound trivial, but in the context of the cosmic microwave background, those minute variations matter deeply. They are the fingerprints of the early universe, imprints of density differences that shaped all later structure. The cold spot, however, was too large and too deep to arise easily from random fluctuations. When scientists generated thousands of simulated universes under the standard cosmological model, almost none contained such a feature. The first explanation proposed was elegant. Perhaps there was a massive cosmic void between us and that patch of ancient light. As a photon passes through a region of lower density, it can lose energy due to what is known as the integrated Sachs-Wolf effect. Entering a void, it gains a bit of energy from the local gravitational potential. But as the universe expands, that potential stretches, and the photon leaves slightly weaker than before, its wavelength elongated, its temperature lower. In 2015, astronomers studying the region with data from the Dark Energy Survey and the WISE infrared maps found hints of an enormous underpopulated zone, roughly 2 billion light-years across, located in the direction of the constellation Eridanus. It was named the Eridanus supervoid and briefly hailed as the answer. The cold spot, they suggested, was the faint shadow of this cosmic emptiness. Yet simulations showed that even such a vast void could not produce the full cooling seen in the data. The numbers refused to align. The cold spot was still too deep, too coherent, and too statistically improbable. The supervoid might be part of the cause, but not the entire story. Some cosmologists concluded that the anomaly might simply be a cosmic coincidence, a random fluctuation with no deeper meaning. In a sky covering billions of degrees of arc, one patch might just, by chance, stray further from average than expected. But others sought a more fundamental reason. They turned to the physics of inflation, the period of rapid expansion in the universe's first moments. Quantum irregularities during inflation were stretched to cosmic scales, leaving subtle scars in the microwave background. If the inflationary field fluctuated in an unusual way, it could have left behind an isolated region with slightly different energy density, perhaps the cold spot itself. The most daring idea suggested that the cold spot might be a mark left by a collision between universes. In some inflationary models, our cosmos is one bubble among many, each with different physical constants. If two such bubbles met in their infancy, the impact could leave a circular signature on the cosmic microwave background, a visible bruise in space-time. The cold spot matches what such a collision might produce, though there is, for now, no observational evidence for other universes beyond theory. Planck's detailed maps, especially those measuring polarization, have refined the cold spot structure. The data suggest a combination of factors: a modest contribution from the Eridana supervoid, ordinary statistical variance, and perhaps the imprint of unknown physics. There is no single, satisfying answer, only the recognition that the universe still contains puzzles large enough to challenge its own equations. Beyond its scientific intrigue, the cold spot carries quiet symbolism. It is a reminder that the universe, though mostly smooth, is built on tiny imperfections. Those slight irregularities, minute differences in temperature and density, are what allowed matter to clump together, forming galaxies, stars, and eventually life itself. The cold spot, however strange, is an expression of that same principle. From small fluctuations come great structures. Even if it turns out to be nothing more than chance, the anomaly has already earned its place in the story of discovery. It keeps scientists vigilant, forcing them to recheck their models, refine their instruments, and confront the edges of understanding. In a sky that should be seamless, one unlikely patch continues to whisper that creation still holds secrets. The microwave background stretches outward in every direction, a soft, ancient glow shaped by both structure and silence. Following its subtle variations leads us toward the vast cosmic voids where gravity fades and light drifts slowly through emptiness, hinting that the cold spot may be just one chapter in the grand geometry of the universe itself, the map of the ancient light. Across the entire sky lies a faint, uniform glow light that has travelled for nearly 14 billion years. It is not starlight or the reflection of galaxies, but something far more ancient: the cosmic microwave background, or CMB. This is the leftover radiation from the Big Bang, a fossil record of the universe when it was young and dense, filled with a brilliant fog of matter and energy. To map it is to glimpse the moment when light first broke free and began its long journey through time. In the beginning, the universe was an opaque plasma of protons, electrons, and photons locked together by constant collisions. Light could not move freely. It was endlessly scattered in all directions. After about 380,000 years, the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms, a process called recombination. When that happened, photons were finally released into open space. Those same photons still reach us today, their wavelengths stretched by cosmic expansion until they now glow faintly in microwaves. This light, barely 3 degrees above absolute zero, is the earliest image of the universe we can ever see. The CMB was discovered by accident in 1965 by radio engineers Arno Penzias and Robert Wilson at Bell Labs. They were puzzled by a faint hiss that persisted no matter where they pointed their antenna. After ruling out technical faults and even cleaning away nesting pigeons, the noise remained. Meanwhile, just 30 miles away, a Princeton team led by Robert Dicker was preparing to search for the very same radiation predicted years earlier as the Big Bang's afterglow. When the groups compared results, the realization was immediate. The background hum came from the birth of the cosmos itself. In the decades that followed, mapping this ancient light became a central pursuit of modern cosmology. The CMB is remarkably uniform. its temperature averaging 2.725 Kelvin, yet tiny irregularities of only a few millionths of a degree mark, where matter in the early universe was slightly denser. These small fluctuations are the seeds from which every galaxy, star, and planet would later grow. NASA's Cosmic Background Explorer, COBE, launched in 1989, provided the first detailed view of this faint radiation. It confirmed that the CMB matched the perfect black-body spectrum expected of Big Bang relic light, and revealed subtle anisotropies, minute variations across the sky. Those differences were crucial. They showed where gravity would begin pulling matter together, shaping the cosmic landscape. For their work, COBE's scientists John Mather and George Smoot received the Nobel Prize in 2006. The mapping improved dramatically with the Wilkinson Microwave Anisotropy Probe, 2001. It charted the sky with much higher resolution, refining the universe's age to 13.7 billion years, and measuring its composition. Roughly 5% normal matter, 27% dark matter, and 68% dark energy. The data also revealed that on large scales, space is almost perfectly flat, confirming predictions of cosmic inflation, a period of rapid expansion that occurred in the universe's first instant. Then came the Planck satellite in 2009, built by the European Space Agency. With detectors cooled to near absolute zero, Planck measured the sky at multiple frequencies, mapping temperature variations with unprecedented precision. Its results showed a delicate pattern of warm and cool regions, each representing slight density differences in the early universe. These ripples are not random. They carry the signature of acoustic waves, sound vibrations that once rippled through the primordial plasma. In those first moments, matter and radiation were tightly coupled, forming a kind of cosmic fluid. Pressure and gravity pushed against each other, creating sound waves that compressed and expanded the plasma. When the light finally escaped, those vibrations froze into the CMB, leaving behind a pattern of peaks and troughs visible in the data today. By studying these patterns, cosmologists can determine the universe's expansion rate, geometry, and composition with remarkable accuracy. The CMB, in that sense, is both a photograph and a recording of the early universe, preserving the echoes of creation itself. But among this near-perfect uniformity lies an anomaly, the cold spot. First detected in WMAP's maps and confirmed by Planck, it is a vast area, hundreds of millions of light-years across, that appears significantly cooler than its surroundings. Most temperature variations in the CMB are explained by standard models of inflation, yet the cold spot's size and depth make it unusually improbable. Its presence suggests there may be more to the universe's structure or its history than our current models reveal. Every detail in this ancient light tells part of the story. The CMB's patterns reveal how dark matter shaped the cosmic web, how dark energy influences its expansion, and how gravitational waves from the universe's first instant might have rippled through space. Nearly all that we know about the universe's age, density, and evolution comes from decoding this faint radiation, a signal so weak it would be invisible to human eyes, yet it fills all of space. The map of the ancient light is, in essence, the universe's own memory. It records the moment when everything became visible, when chaos gave way to order. Through it, we trace the lineage of galaxies and worlds, back to when the cosmos itself was only a luminous mist. The cold spot, though a small imperfection in this grand design, reminds us that even in the oldest light, mystery endures. And beyond this ancient pattern, The CMB reveals the hidden geometry of the cosmos, the great empty voids where gravity weakens and light fades. It is within those silent expanses that the story of the cold spot continues, hinting that the universe still holds secrets waiting to be found in the faintest light of its beginning. Ripples from creation, the quiet vastness of space. The universe still carries an ancient rhythm, a pattern of ripples that began when everything was new. These are not sound waves as we know them, but cosmic vibrations that once pulsed through a young, glowing universe. In the first few 100,000 years after the Big Bang, matter and light were woven into a single, turbulent plasma. Within that bright fog, gravity and pressure played against one another, creating vast waves that rippled through the early cosmos. When the universe cooled and became transparent, those waves froze in place, leaving behind faint imprints in the cosmic microwave background in the earliest record of the universe's structure. In that young era, light could not yet move freely. Photons collided constantly with charged particles, trapped in an endless scattering. But the universe was not perfectly even. Tiny fluctuations in density, remnants of quantum variations stretched during inflation, gave gravity something to work with. Matter was drawn inward, compressing some regions, while radiation pushed outward, creating a counterforce. The result was a vast interplay of pressure and gravity, waves of compression and expansion spreading through the plasma at half the speed of light. These acoustic ripples filled the universe, like sound reverberating through a vast cosmic instrument. When the universe reached about 380,000 years of age, it cooled enough for protons and electrons to combine into neutral atoms. Light was finally freed to travel through space, capturing a snapshot of those vibrations in motion. Those photons became the cosmic microwave background, and the temperature variations we now see, slightly warmer or cooler patches across the sky, are the fossilized traces of those ancient sound waves. The data collected by satellites, such as COBE, WMAP, and Planck, revealed that these ripples follow an elegant mathematical pattern. When scientists plotted the CMB's temperature variations, they found a series of peaks, each representing a particular note in the universe's early symphony. The first peak marks regions where matter was most compressed under gravity. The next peaks show where pressure pushed back. Together, they form a perfect balance between collapse and rebound, a frozen harmony written across the cosmos. By studying these peaks, cosmologists can deduce extraordinary details about the universe. Their positions and heights reveal its age, shape, and composition. The data show that the universe is about 13.8 billion years old, composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. The spacing of the peaks even confirms that the geometry of space is almost perfectly flat, a striking validation of the theory of cosmic inflation, which proposed that the universe expanded exponentially in its first instant, stretching tiny fluctuations to cosmic scales. What is remarkable is how small these variations are. The temperature differences across the CMB amount to just 1 part in 100,000. Yet from those minute irregularities grew everything, the galaxies, the clusters, and the vast filaments that shape the universe today. Regions that began slightly denser became gravitational anchors for stars and planets. The slightly emptier regions expanded into immense cosmic voids. The modern universe, in all its structure and variety, is the magnified echo of these first ripples from creation. These waves also left their mark in another subtle way, through polarization. As the light from the CMB scattered off the last free electrons, it acquired a faint directional pattern. Within that polarization, scientists search for traces of an even older phenomenon, gravitational waves, generated during the universe's first moments. Detecting those primordial ripples in space-time would provide direct evidence of inflation and reveal how quantum processes shaped the birth of everything we know. But even this cosmic harmony is not without its peculiarities. Amid the delicate balance of temperature variations lies an anomaly, the cold spot. First observed in data from WMAP and confirmed by Planck, it is a region unusually large and cool, standing out like a soft discordant note in an otherwise perfect composition. Whether caused by a vast cosmic void, a rare fluctuation, or something deeper, it remains one of the universe's most intriguing mysteries. The ripples from creation form the foundation of cosmic architecture. Every star and galaxy traces its origin to those primordial vibrations, to that moment when energy, matter, and gravity first found rhythm together. They are the universe's oldest signature, a melody frozen in light, stretching across billions of years to reach us now. Traces of those first waves still shape the vast cosmic web. Following them outward leads into the immense underpopulated regions that punctuate the universe, places where gravity fades and light slows its pace, and where the enigma of the cold spot begins to unfold in the quiet geometry of emptiness. The echo of the Big Bang. The night sky lies a faint, uniform glow that surrounds everything. It is not starlight, nor the shimmer of galaxies, but something far older, the cosmic microwave background, the first light ever released by the universe. This ancient radiation, faint and cold, is the lingering echo of the Big Bang. It has travelled through space for nearly 14 billion years, stretched and softened by the universe's expansion, until it now glows just a few degrees above absolute zero. In its earliest moments, the universe was a blazing plasma of energy and particles, protons, electrons, and photons, locked together in constant collision. Light could not travel freely through this dense fog. But as space expanded, it cooled. Around 380,000 years after the Big Bang, the temperature dropped enough for protons and electrons to combine into neutral hydrogen atoms. With this recombination, light was freed to move unhindered. Those first photons have been travelling ever since, forming the afterglow we detect today as the cosmic microwave background, the universe's oldest visible memory. The discovery of this ancient radiation came by accident in 1965. Two engineers at Bell Labs, Arno Penzias and Robert Wilson, detected a faint background hiss that persisted no matter where they pointed their antenna. They ruled out interference, cleaned their equipment, even removed pigeons nesting inside, yet the signal remained. Nearby, at Princeton University, physicists led by Robert Dick were preparing to search for just such a signal predicted as the cooled remnant of the Big Bang. When the two teams compared notes, the mystery was solved. The faint hiss was the leftover heat of creation itself. This discovery confirmed that the universe began in a hot, dense state and has been expanding ever since. The radiation was measured at a temperature of 2.7 Kelvin, matching the predictions for relic light from the early cosmos. It also showed remarkable uniformity evidence that the universe was nearly the same everywhere in its infancy. Yet later observations revealed faint irregularities, only a few millionths of a degree different from one region to another. Those tiny variations were the seeds of everything to come: galaxies, stars, and planets. NASA's Cosmic Background Explorer, COBE, launched in 1989, was the first mission to measure these temperature fluctuations precisely. It confirmed that the CMB had the perfect blackbody spectrum expected from the Big Bang, and it detected small anisotropies, tiny warm and cool patches across the sky. These minute ripples were the fingerprints of structure, showing where gravity had begun to pull matter together. For this discovery, COBE scientists John Mather and George Smoot later received the Nobel Prize in Physics. In 2001, the Wilkinson Microwave Anisotropy Probe, WMAP, produced a far more detailed map of the CMB, refining the universe's age to about 77 billion years. Its data revealed the cosmos's composition, roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. WMAP also confirmed that the geometry of space is nearly flat, supporting the theory of cosmic inflation, a brief burst of expansion that occurred fractions of a second after the Big Bang. Then, in 2009, the European Space Agency's Planck satellite offered the clearest view yet. With detectors cooled to near absolute zero, it measured the CMB at multiple frequencies, removing interference from dust and gas. The resulting map displayed a mottled pattern of faint temperature variations, echoes of pressure waves that once rippled through the early plasma. Each peak and trough marks the balance between gravity pulling matter inward and radiation pushing outward. These frozen oscillations formed the universe's first structure, a cosmic rhythm still visible in the data today. From these, cosmologists can read the universe's entire blueprint, its age, shape, composition, and expansion rate. The patterns confirm that space is flat and that the cosmos has been expanding under the influence of dark energy. The smallest temperature differences, only 1 part in 100,000, became the framework for everything that exists, proof that vast complexity arose from near-perfect simplicity. Yet within this near-uniform light lies an anomaly, the cold spot. First seen in WMAP's data and later confirmed by Planck, it is an unusually large and cold region of the CMB, stretching hundreds of millions of light-years across. Its size and depth defy statistical expectations. Some scientists believe it may be the shadow of a vast cosmic void, where light lost energy while passing through sparse regions of space. Others suggest it could be evidence of new physics, or even the faint signature of a collision between universes in the earliest moments of inflation. The cosmic microwave background is far more than an ancient glow. It is the universe's autobiography, written in temperature and light. Every detail encodes a story: how space expanded, how gravity sculpted matter, and how energy cooled into form. It is the boundary between opacity and transparency, chaos and structure, silence and sound. Even now, this faint radiation surrounds us, filling every corner of space and every gap between galaxies. It connects the atoms of our bodies to the first fire of creation. Within it lies both our origin and our context, a quiet reminder that all we see began as light released into a still-forming cosmos. And as we trace this ancient signal across the heavens, its subtle variations guide us toward the larger structures that followed, toward the great cosmic voids, and the mysterious cold spot that breaks the pattern of perfection, hinting that the universe's story may be stranger and deeper than we can yet imagine. Why the universe isn't uniform. At first glance, the universe seems remarkably even. The cosmic microwave background, the afterglow of the Big Bang, spreads across the sky with astonishing smoothness, its temperature almost identical in every direction. Yet hidden within that uniformity are tiny differences, minute ripples, only a few millionths of a degree apart. Those subtle variations, invisible to the naked eye, are the reason anything exists at all. Without them, there would be no galaxies, no stars, no planets, only an endless, featureless fog of matter. In its earliest moments, the universe was a perfectly balanced ocean of energy. After the Big Bang, space was filled with hot plasma, particles of light, matter, and radiation in constant motion. On large scales, This early cosmos was nearly uniform, but quantum mechanics, the unpredictable realm of subatomic physics, ensured it was never completely so. Tiny fluctuations in energy density emerged, random and spontaneous, scattered throughout the young universe. When cosmic inflation began, a period of rapid expansion that stretched the universe faster than light, these microscopic variations were magnified to cosmic size. What had once been subatomic differences became vast regions slightly denser or thinner than average. Those ripples became the universe's first structure. As the cosmos cooled, gravity began to amplify those differences. In slightly denser regions, matter pulled inward, forming clouds that would one day collapse into galaxies. In less dense areas, matter drifted away, leaving behind the great cosmic voids that now span hundreds of millions of light years. Over billions of years, this gentle imbalance sculpted the large-scale structure we see today, a cosmic web of filaments and clusters surrounded by immense emptiness. The universe's beauty, the stars, galaxies, and nebulae, was born from imperfection. Astronomers can still see evidence of those first ripples in the cosmic microwave background. The temperature variations, mapped by satellites like WMAP and Planck, correspond precisely to differences in density in the early universe. Regions that appear slightly warmer mark where the plasma was denser and photons were trapped longer in gravitational wells. Cooler regions mark where it was thinner and light could escape more easily. These patterns are the blueprint of all later structure, showing how random quantum fluctuations evolved into the galaxies we observe across the night sky. The degree of variation is surprisingly small, about 1 part in 100,000, yet that was enough. If the universe had been perfectly smooth, gravity would have had nothing to work with, and matter would never have clumped. On the other hand, if the irregularities had been much stronger, the cosmos would have collapsed on itself long before galaxies could form. The balance was exquisite, just enough unevenness to give rise to complexity, but not enough to destroy it. Scientists describe this distribution statistically using what's called the power spectrum of the cosmic microwave background. It shows how the size and strength of fluctuations vary across different scales. The pattern fits remarkably well with predictions from inflation theory, an elegant confirmation that the same quantum mechanics guiding the tiniest particles also shaped the entire universe. These fluctuations are thought to arise from random quantum fields stretched across space during inflation, their energy differences frozen into the fabric of the cosmos as it expanded. Over time, as matter cooled and dark matter began to dominate gravitationally, these small density variations grew. Dark matter, invisible but abundant, acted as scaffolding around which normal matter could collect. Hydrogen gas pooled into those gravitational wells, cooling and condensing until the first stars ignited. From those stars came heavier elements, carbon, oxygen, iron, the ingredients for planets and life. Every galaxy, every cluster, and every human being owes existence to the fact that the universe began slightly uneven. Even today, this unevenness defines cosmic structure. When astronomers map galaxies across billions of light years, they find a vast web of filaments and nodes, with enormous empty regions, voids between them. It's a pattern of remarkable consistency, echoing the temperature map of the early universe almost perfectly. The smallest fluctuations seen in the CMB have become the largest structures in space, stretched by gravity over cosmic time. And yet, there are anomalies that push at the edges of this order. The cold spot, for example, appears as a region of the cosmic microwave background far colder and larger than typical fluctuations predict. It may represent an unusually vast void, or something stranger perhaps, a statistical outlier, or even evidence of new physics beyond our current models. Whatever its cause, it highlights that the universe's apparent symmetry still hides mysteries that reach back to its birth. In essence, the universe isn't uniform because perfection is unstable. A perfectly smooth cosmos could not have evolved. It would have remained an eternal haze. The unevenness born from quantum randomness gave the universe texture, allowing matter to gather, cool, and ignite. Those minute imperfections, fractions of a degree in the microwave sky, are the reason stars burn and galaxies spin. The faint irregularities etched into the ancient light reveal not chaos, but an elegant balance between order and disorder, a balance that allowed the universe to become structured, luminous, and alive. Far beyond the glow of galaxies, the same delicate variations continue to shape space itself, guiding us toward the immense voids and hidden geometries where the cold spot quietly lies, waiting to reveal what deeper imperfection might still linger in the universe's design. The great supervoid. Beyond the glittering chains of galaxies lies a region where almost nothing exists, a cosmic desert so vast and empty that light itself grows weary as it crosses. Astronomers call it the Great Supervoid, an enormous stretch of space that may hold clues to one of the universe's strangest mysteries, the cold spot. It is not truly devoid of matter, but compared with the crowded filaments and clusters that fill much of the cosmos, it is profoundly underpopulated. The galaxies here are sparse, the distances between them immense, and the gravitational pull faint. Voids like this are normal features of the large-scale universe. On cosmic maps, galaxies form vast webs of structure, strung along filaments that meet at glowing knots, superclusters of countless galaxies. Between these filaments lie enormous empty regions called voids, where matter is thin and gravity weak. Most voids stretch tens or hundreds of millions of light-years across, but the Great Supervoid dwarfs them all. Measuring roughly 2 billion light-years wide, it is one of the largest known structures of its kind, an immense underdense bubble that spans a significant portion of the observable cosmos. The story of its discovery began when astronomers noticed the cold spot, a puzzling patch of the cosmic microwave background that appeared slightly cooler than expected. The anomaly was first detected by the Wilkinson Microwave Anisotropy Probe in 2001, and later confirmed by the Planck satellite in 2013. The cold spot's size and depth defied ordinary statistical expectations. It was too large and too coherent to fit comfortably within the standard cosmological model. Searching for a possible cause, scientists turned their gaze to the region of sky that corresponded to it, in the direction of the constellation Eridanus. What they found there was astonishing, a vast emptiness, unlike anything else nearby. Using data from surveys such as the Sloan Digital Sky Survey and the Dark Energy Survey, astronomers mapped the distribution of galaxies across this region and identified a significant underdensity extending across hundreds of millions of light-years. It became known as the Eridanus supervoid. Later observations with infrared instruments, including NASA's Wide Field Infrared Survey Explorer, WISE, confirmed the same vast absence, suggesting that the void might indeed be connected to the cold spot. To understand how a void could influence the cosmic microwave background, one must look to a subtle effect called the integrated Sachs-Wolf effect. As photons from the CMB travel through the universe, they encounter varying gravitational fields caused by regions of different density. When a photon enters a dense area, it gains energy falling into the gravitational well. When it climbs out, it loses the same amount, leaving its energy unchanged. But in a universe whose expansion is accelerating, driven by dark energy, the gravitational potential itself weakens over time. This means a photon leaving an underdense region, like a supervoid, does not lose as much energy as it gained on entry. The result is a slight reduction in its temperature when it finally reaches us. If the great supervoid lies along the line of sight to the cold spot, its vast underdensity could, in theory, cause the observed cooling by this mechanism. However, detailed models suggest that even such a massive void would only account for a fraction of the temperature difference. The cold spot appears too pronounced to be explained entirely by the void's influence. The great supervoid may contribute to the anomaly, but it cannot fully create it. Still, the void itself remains a remarkable structure, a relic of the universe's earliest fluctuations. Cosmologists believe such enormous underdensities formed from the same tiny variations in density, imprinted on the cosmic microwave background. As the universe expanded, gravity drew matter toward denser regions, leaving the thin areas even emptier. Over billions of years, this process exaggerated the contrasts, producing the immense cosmic web we see today. The great supervoid is the quietest part of that web, a region defined not by what it contains, but by what it lacks. Studying these cosmic voids offers more than curiosity. They act as natural laboratories for testing cosmological models and the effects of dark energy. Because the expansion of space is less opposed by gravity inside voids, these regions grow faster than the denser surroundings. By observing their size, shape, and rate of expansion, astronomers can probe how dark energy behaves over time. The Great Supervoid, being one of the largest known examples, provides an especially valuable window into this aspect of the cosmos. Though it cannot alone explain the cold spot, the Great Supervoid reveals how the universe's vast structure shapes the light that travels through it. Every photon passing across its emptiness is subtly stretched, cooled, and delayed, its journey marked by the absence of matter. In this way, the void quietly sculpts the background glow of the universe, leaving faint imprints that hint at its immense scale. In the grand cosmic tapestry, the great supervoid is a pause between patterns, a silence between the notes of creation. Its stillness is as important as the galaxies that surround it, for without emptiness, structure itself could not exist. And beyond this deep hollow, the universe continues to unfold, revealing other vast anomalies that challenge our understanding of cosmic balance. From the heart of this immense nothingness, our gaze extends outward again, toward the delicate filaments that bridge these voids, threads of matter that bind the cosmos together in a web of light and gravity. A hole in space, galaxies weave together into filaments and clusters. There exists a region that defies expectation, a vast, dim stretch of near emptiness that astronomers have come to call a hole in space. It is not a black hole, nor any kind of violent gravitational anomaly, but a literal void, a cosmic volume almost completely devoid of matter. Where we expect to find the ordinary pattern of galaxies, clusters, and light, there is instead a silence that stretches for billions of light years. This immense underdensity first drew attention when scientists studying the cosmic microwave background noticed a patch that appeared unusually cold, the so-called cold spot. To understand why that region of sky seemed to radiate less warmth, astronomers turned to maps of galaxy distributions, expecting to find an explanation written in the structure of the nearby universe. What they found was startling. Along the line of sight to the cold spot lies one of the largest known cosmic voids, an expanse so empty it could swallow thousands of galaxies without leaving a trace. the existence of such a void is not, in itself, mysterious. The universe on large scales is far from uniform. Matter clusters under gravity, forming filaments, walls, and nodes, the great cosmic web that defines the structure of space. Between those luminous threads lie the voids, regions where gravity has pulled matter away, leaving only sparse remnants of hydrogen gas and a scattering of lonely galaxies. Most voids are 100 or 200 million light-years across. The one aligned with the cold spot, however, spans nearly 2 billion light-years, so large that it challenges the statistical limits of what our cosmological models predict. This vast region, often referred to as the Eridanus supervoid, sits hundreds of millions of light-years from Earth. Surveys conducted using the Dark Energy Survey and NASA's WISE infrared observatory revealed the striking absence of galaxies there. Where the rest of the cosmos appears textured with clusters and filaments, this region shows a noticeable dimming, an emptiness deep enough to affect the light that passes through it. The key to understanding how a void might create a cold imprint on the cosmic microwave background lies in a subtle physical effect known as the integrated Sachs-Wolf effect. As CMB photons, the relic light from the Big Bang, travel through the universe, they pass through regions of differing gravitational potential. When a photon enters a dense cluster, it gains energy falling in and loses the same amount climbing back out, leaving its temperature unchanged. But if the universe's expansion is accelerating, as it is today due to dark energy, these gravitational wells and hills change shape over time. A photon crossing a vast, underdense region, like the Eridanus void, exits slightly cooler than it entered. It loses a fraction of its energy because the gravitational hill it climbed has weakened during its journey. This subtle cooling may explain part of the cold spot's unusual temperature. Yet calculations show that even a void of this immense size could account for only a portion of the observed anomaly. The rest remains unexplained, leaving cosmologists to wonder whether the cold spot represents an improbable statistical fluctuation or something more exotic, perhaps a relic of interactions between universes in the early moments of cosmic inflation. Despite its mystery, the hole in space offers a rare opportunity to study the universe's architecture. Cosmic voids are, in many ways, as important as the galaxies that define their borders. They make up the majority of the universe's volume, forming a hidden scaffolding of nothingness that influences how matter clusters and how light travels. In these regions, the expansion of the universe is less resisted by gravity, meaning voids grow faster than the surrounding structures. Their shapes and distribution hold clues to the properties of dark energy and the rate of cosmic acceleration. Observations suggest that galaxies found near the edges of voids are slightly different from those in denser environments. They tend to form fewer stars, and their structures are less disturbed, evolving slowly in their tranquil isolation. For astronomers, studying them is like listening to the universe's quietest notes, tracing how gravity and emptiness compose the larger cosmic melody. There is also something profoundly humbling about such emptiness. The great supervoid is not a tear in the fabric of space, nor a gap in creation. It is the natural consequence of how matter flows under gravity, collecting in some places and leaving others bare. Yet, in its vast silence, it challenges our intuition about what nothing means. Even here, in a region nearly devoid of galaxies, there is still the faint glow of background radiation, the whisper of particles, and the steady expansion of space itself. The hole in space reminds us that the cosmos is as much defined by its absences as by its abundance. The luminous threads of galaxies gain meaning only against the backdrop of the voids between them. And as the cold spot continues to puzzle astronomers, This immense region of emptiness remains one of the most evocative landscapes in the universe. A place where light weakens, gravity softens, and the quiet geometry of space stretches toward infinity. Beyond this vast hollow, the filaments of matter resume their dance, linking clusters and galaxies across the cosmic web. Following those luminous strands outward leads us from emptiness back into structure, toward the immense bridges of matter that bind the universe together in light and gravity. Light that lost its way. Long before galaxies had formed and stars began to burn, light was already on its journey. It moved freely across a young universe, still expanding, still cooling, still defining what space would mean. Those photons, remnants of the Big Bang, became the cosmic microwave background, a faint bath of radiation that fills the sky even now. For nearly 14 billion years, this ancient light has travelled undisturbed through space, carrying within it the story of creation. Yet, along the way, some of that light encountered obstacles, vast, invisible structures that warped and delayed it. In certain regions, its path was stretched, its energy drained, and its warmth diminished. It became light that quite literally lost its way. When astronomers study the cosmic microwave background, they're not just observing a picture of the universe as it once was, they're seeing how that ancient light has been shaped by everything it has crossed since. Every photon that reaches us has travelled through an evolving landscape of galaxies, clusters, and cosmic voids. Each structure subtly alters the light's temperature and direction through the force of gravity. These effects, while minute, are measurable, and they tell us about the large-scale architecture of the universe. Among them, one phenomenon plays a key role in explaining the curious coolness of the cold spot, the integrated Sachs-Wolf effect. This effect arises because light does not travel through a static universe. As it moves through a region of space with different densities, it experiences shifts in gravitational potential. Imagine a photon passing through a dense cluster of galaxies. It falls into the gravitational well, gaining a little energy, then loses that energy climbing out. In a perfectly balanced universe, those two effects would cancel out. But our universe isn't static, it's expanding, and that expansion is accelerating under the influence of dark energy. As a result, the gravitational wells and hills change shape while light is still moving through them. A photon leaving a large void or cluster does not emerge with quite the same energy it entered with. In the case of the cold spot, the light appears slightly cooler than average because it likely passed through an enormous region of underdensity, a supervoid on its journey to us. Inside a void, there's less matter to create gravity, so the gravitational potential weakens more quickly as the universe expands. A photon falling into this shallow potential well gains a bit of energy, but when it climbs out, it loses more than it gained. By the time it reaches our telescopes, it's a fraction of a degree cooler, its wavelength stretched ever so slightly longer. This process doesn't just create temperature differences, it encodes a map of the universe's invisible scaffolding. The pattern of tiny temperature fluctuations across the CMB reveals where light has been slowed, bent, or cooled. It's through this lens that astronomers have traced vast cosmic structures otherwise invisible to ordinary observation. The cold spot, however, stands out as unusually large and coherent, even accounting for the Sachs-Wolf effect. The degree of cooling it shows seems to exceed what a single void could produce. The light that formed it appears to have wandered through a region stranger and emptier than expected, as though space itself had stretched more there than anywhere else. Some researchers suggest that the light's detour through the Eridanus supervoid, spanning nearly 2 billion light-years, accounts for part of the anomaly. Yet simulations of the known universe show that even such a colossal emptiness should not create a temperature dip as pronounced as the cold spots. Others propose that multiple smaller voids may lie along the same line of sight, their effects stacking to produce a deeper cooling. In this view, the cold spot isn't one event, but a chain of coincidences, light delayed and drained by a series of cosmic absences. Whatever the cause, this wandering of light through changing gravitational landscapes provides a vivid reminder of how dynamic the cosmos truly is. Space is not a smooth, empty canvas. It's a vast terrain of hills and valleys, sculpted by matter and dark energy alike. Every photon is a traveller moving through that uneven terrain, its path subtly deflected by gravity, its energy shaped by expansion. The cold spot may be one of the most dramatic examples of what happens when that journey passes through an extreme landscape, a vast emptiness where even light struggles to hold its warmth. In the broader picture, these distortions are not mere curiosities. They are the universe's natural record of its own evolution. By studying how light has changed, scientists can infer how dark energy accelerates cosmic expansion, how galaxies form and cluster, and how structure continues to grow over billions of years. The universe, in this sense, is its own storyteller, using photons as messengers to carry information across time. And somewhere in that great message lies the faint trace of the cold spot light that lost its way, slowed by the emptiness it crossed, dimmed by the expansion it could not resist. It arrived weaker but more meaningful, a record of cosmic geography carved in temperature and wavelength. Beyond this faint scar in the sky, other distortions ripple outward signals from gravitational waves, lensing effects, and still deeper anomalies waiting to be found. Following these shifting paths of ancient light leads us further through the web of the universe, where space itself bends and stretches, and where the journey of every photon continues to map the hidden shape of the cosmos. Dark energy's hidden hand. The universe is not merely expanding, it is accelerating. Every distant galaxy drifts away faster than it did the moment before, as though some invisible pressure pushes outward from the fabric of space itself. This unseen influence, discovered at the turn of the millennium, is known as dark energy. And though it dominates the cosmos, we still have no clear idea what it truly is. It acts everywhere, yet leaves no trace, shaping the grand architecture of the universe while remaining utterly intangible. And within that invisible motion lies a clue to one of the cosmos's deepest mysteries, the strange chill of the cold spot. To understand dark energy's influence, one must first grasp how expansion behaves under gravity. For much of cosmic history, the universe's growth was slowing, its rate of expansion gradually checked by the mutual attraction of all matter. Galaxies pulled gently on one another across unimaginable distances, and though the universe continued to grow, its pace steadily declined. Then, about 5 billion years ago, something changed. Observations of distant supernovae revealed that the expansion was no longer decelerating, it was speeding up. The galaxies were not simply drifting apart, they were accelerating away from each other. This discovery, made independently by 2 research teams in 1998, overturned everything we thought we knew about cosmic evolution. The simplest explanation was that empty space was not truly empty. Einstein had once introduced a term in his equations called the cosmological constant, a subtle mathematical addition meant to keep the universe stable and unchanging. He later discarded it when the universe was found to be expanding, calling it his greatest blunder. Yet, decades later, that discarded idea became the best description of dark energy, a property of space itself, an energy inherent to the vacuum that grows stronger as the universe expands. It does not push in the traditional sense, rather, it stretches the geometry of space, causing distant galaxies to recede ever faster. This quiet but relentless acceleration affects more than galaxies. It reshapes how light travels, how matter gathers, and how vast structures evolve. When cosmic microwave background photons, the afterglow of the Big Bang, cross regions of differing density, they experience subtle shifts in energy. In a universe governed only by gravity, these shifts would balance out. But dark energy alters the balance, changing gravitational potentials as space expands. This is the integrated Sachs-Wolf effect, the same mechanism that likely contributes to the mysterious coolness of the cold spot. As light from the early universe passes through a massive cosmic void, it gains energy falling in, but loses slightly more climbing out because the void has expanded and its gravitational well has weakened during the photon's journey. The result is a cooler patch of microwave light when that photon finally reaches us. In this way, dark energy exerts a hidden hand across the cosmic landscape. It does not create the voids themselves, but it amplifies their influence, deepening the contrast between emptiness and structure. Over billions of years, it stretches the gaps between filaments of matter, thinning the cosmic web and allowing vast underdense regions like the Eridanus supervoid to grow even larger. These expanding voids subtly distort the background radiation, leaving faint fingerprints like the cold spot signatures not of chaos, but of a universe driven by an invisible pressure. The presence of dark energy also changes how we perceive time and distance on cosmic scales. Because expansion accelerates, light from distant galaxies must travel ever farther to reach us. The photons we detect today have crossed regions of space that have been stretching throughout their journey, diluting their energy and redshifting their wavelengths. What we see as cooling in the microwave background is not merely the relic temperature of the early universe, but the cumulative effect of billions of years of expansion sculpted by dark energy. Despite its enormous influence, dark energy remains one of science's great enigmas. It makes up roughly 68% of the total energy content of the cosmos, yet we cannot detect it directly. It may be a cosmological constant, as Einstein proposed a steady pressure pervading space, or it might evolve over time, linked to a field that changes with the universe's expansion. Some theories even suggest that dark energy hints at new physics beyond our current understanding, a clue to deeper forces governing the cosmos. In the context of the cold spot, dark energy provides a quiet but plausible explanation for part of the anomaly's cooling. The photon's long journey through expanding voids is guided by this hidden hand, which weakens gravitational wells and alters the path of ancient light. Without dark energy, the cold spot might not exist as we observe it. The universe's acceleration is what allows such large, underdense regions to form and persist. Yet, even with this understanding, the anomaly's size and coherence still challenge the limits of what dark energy alone can explain. Dark energy is not dramatic, it is patient. Its influence builds over eons, changing the universe in silence. Galaxies drift farther apart, cosmic voids widen, and the light of the early universe cools as it travels through an ever-expanding sea of space. Its effects are cumulative, subtle, and inescapable. In the end, the hidden hand of dark energy reminds us that emptiness is not passive. It is an active, dynamic part of the universe's design, a silent architect shaping everything from the fate of galaxies to the faintest temperature variations in the sky. And as this expansion continues, the cosmos will only grow colder and more isolated, until even the relic light of the Big Bang fades into darkness. From the quiet influence of dark energy, our gaze turns to what it leaves behind, the thinning web of matter stretched across the universe, where gravity still clings to what remains of light and structure amid the deepening cosmic void. the cosmic mirage. In universe, light rarely travels in a straight line. It bends and twists as it moves through the invisible curves of gravity, like a traveller crossing shifting dunes of spacetimes. This bending of light, known as gravitational lensing, is one of the universe's most elegant illusions, a natural mirage shaped not by heat and air, but by mass and geometry. Through this effect, gravity itself acts as a cosmic lens, distorting, magnifying, and sometimes multiplying the appearance of distant galaxies. It allows us to see objects otherwise far too faint or remote, and in doing so, it reveals the hidden structure of the cosmos. Einstein predicted this phenomenon in 1915 when he formulated his general theory of relativity. According to his equations, massive objects such as galaxies and clusters warp the very fabric of space around them, curving the paths of light that pass nearby. The effect was first confirmed in 1919 during a solar eclipse, when starlight grazing the sun appeared slightly displaced from its true position, just as Einstein's theory had foretold. Since then, gravitational lensing has become one of astronomy's most powerful tools. It allows scientists to map dark matter, measure cosmic expansion, and even peer into the distant past, observing galaxies as they appeared billions of years ago. In a sense, the entire universe is filled with subtle lensing. Every beam of light that reaches our telescopes has been bent by the gravity of galaxies, clusters, and vast dark matter filaments. The image of the cosmos we see is not a direct photograph, but a complex mosaic of distortions. In some regions, gravity magnifies light, like a glass lens, creating bright arcs or multiple copies of the same distant object. In others, it stretches and smears the image, making distant galaxies appear as faint, elongated shadows. These distortions tell a story. They trace the distribution of mass, both visible and invisible, throughout the universe. But lensing does more than reveal what's there. It can also create illusions that complicate what we think we see. In the case of the mysterious cold spot, gravitational lensing might play a subtle but significant role. As ancient light from the cosmic microwave background travels across billions of light years, it passes through countless gravitational wells and voids. Each encounter slightly alters its direction and energy, creating minute temperature variations in the background radiation. Over vast distances, these small deflections accumulate, shaping the smooth map of the early universe into the mottled pattern we observe today. Most of these variations are consistent with standard cosmology, but the cold spot remains unusually large and coherent. Some researchers suggest that what we see might not be an intrinsic feature of the early universe at all, but rather a mirage, an illusion produced by gravitational effects along the light's journey. If a network of massive structures or voids lies along the same line of sight, their combined influence could subtly dim or distort the background radiation, producing a colder region in the microwave sky. The universe, in essence, may be tricking us, bending ancient light just enough to create the appearance of an anomaly where none originally existed. Gravitational lensing can also amplify light from hidden sources behind the cold spot, masking their contribution to the microwave signal. In 2017, studies using data from the Planck satellite and the Dark Energy Survey revealed that the area surrounding the cold spot corresponds to a vast underdense region, the Eridanus supervoid. The gravitational geometry of this void could alter the passage of light in a way that mimics a deeper temperature depression. The photons that crossed it lost a fraction of their energy due to the changing gravitational potential. A phenomenon known as the integrated Sachs-Wolf effect and lensing might enhance or extend that cooling by redistributing the light around the void's edges. The result? A faint optical illusion written on the universe's oldest canvas. Lensing doesn't always produce coldness. It can also brighten and magnify. Massive clusters, for instance, can focus light from galaxies behind them into luminous arcs, allowing us to see structures that existed when the universe was only a fraction of its current age. The Hubble Space Telescope has captured some of the most striking examples, rings of distorted starlight known as Einstein rings, where gravity bends light into nearly perfect circles. These images serve as cosmic magnifying glasses, turning the vastness of the universe into a grand optical experiment. Yet, in the case of the cold spot, the effect seems to work in reverse, dimming rather than amplifying the light, like a shadow cast by the uneven shape of space-time itself. The study of gravitational lensing has become one of the most precise methods for probing dark matter and dark energy, the two unseen forces that dominate cosmic evolution. By analysing how light is bent across different regions of space, astronomers can map where matter resides, even when it emits no light at all. Weak lensing, the gentle distortion of galaxy shapes across large scales, reveals how dark matter forms the skeleton of the cosmic web. Strong lensing, where light is dramatically bent by massive clusters, allows scientists to measure how gravity behaves across billions of years of cosmic history. Together, these techniques transform the universe into a laboratory for testing relativity itself. In the grand view, gravitational lensing reminds us that what we see is not always what truly is. The universe, in its immensity, refracts its own image, reshaping reality through the gentle pull of gravity. The cold spot may yet prove to be a kind of cosmic mirage, a trick of light stretched and cooled by the geometry of emptiness, not a rupture in the laws of physics. Beyond this illusion, other distortions continue to ripple across the cosmic web. Following the subtle bending of ancient light leads us deeper into the interplay between matter and gravity, toward the vast structures that sculpt the universe's hidden shape and reveal how the fabric of space-time itself continues to shift. Beneath the glow of creation, when universes collide, when the universe was still a fraction of a second old, it may not have been alone. According to one of the most ambitious ideas in cosmology, our universe could be just one bubble in an endless cosmic sea, a vast multiverse, where each bubble expands with its own laws of physics and its own beginning. Most of these bubbles would drift apart forever, their edges receding faster than light. But sometimes, in the earliest moments after creation, two might collide. Such an encounter, violent beyond imagining, could leave a scar, a faint, circular mark, imprinted on the background radiation of the cosmos. And to some cosmologists, the cold spot might be just that. The fingerprint of another universe brushing against our own. The notion of colliding universes emerges naturally from the theory of cosmic inflation. Inflation describes the brief period immediately after the Big Bang, when space itself expanded exponentially, driven by a field of energy called the inflaton. This rapid expansion smoothed the universe, ironing out irregularities and explaining why the cosmic microwave background looks so uniform. Yet, in many versions of inflation, this process doesn't stop everywhere at once. Instead, inflation continues eternally in most regions, while small pockets like ours stop inflating and form individual universes. Each one inflates out of the surrounding vacuum like a bubble in a cosmic foam. This framework, known as eternal inflation, suggests that new universes are constantly forming, each with its own vacuum state, energy density, and possibly even different fundamental constants. If this is true, collisions between these expanding bubbles become inevitable. When two universes meet, the energy of their encounter would release immense radiation, distorting space-time where their boundaries touch. Within our universe, such a collision might appear as a circular anomaly on the cosmic microwave background, a subtle region where the temperature is slightly different from its surroundings. In theory, this imprint would persist for billions of years, long after the rest of the universe had settled into equilibrium. The cold spot, first detected by WMAP and later confirmed by Planck, has precisely the qualities that such a collision might produce. It is large, coherent, and unexpectedly deep compared with the random fluctuations expected from standard cosmology. Some researchers, including those exploring models of eternal inflation, have proposed that the cold spot could represent a cosmic bruise, where our universe once brushed against another in its infancy. The boundary between the two would have sent waves rippling through the primordial plasma, leaving a circular mark visible today in the microwave sky. Mathematically, such a collision could be described by solutions to Einstein's equations that link two expanding spacetimes through a shared interface. The details depend on the energy difference between the universes. If the neighbouring universe had a slightly different vacuum energy, the collision would create a disturbance, a shockwave of sorts, that propagates through our early universe. These waves would alter the density and temperature of matter in the affected region, eventually freezing into the cosmic microwave background we see today. Testing this hypothesis, however, is extraordinarily difficult. The patterns produced by a bubble collision would be subtle, nearly indistinguishable from random fluctuations or large-scale statistical anomalies. The cold spot could just as easily arise from a supervoid, a chance alignment of temperature variations, or the normal tale of cosmic probability. Nonetheless, physicists have searched the CMB for circular signatures consistent with the multiverse model. In 2011, a team led by Stephen Feeney analysed WMAP data and found tentative hints of several such rings. Later analyses with Planck data offered mixed results. Some features resembled predictions of collisions, while others fit comfortably within expected random noise. The evidence remains tantalising but inconclusive. What makes the idea so captivating is that it provides a bridge between cosmology and fundamental physics. The mechanism behind inflation is still uncertain, and models that produce multiple universes could help explain why our universe has the physical constants it does. The values that permit stars, chemistry, and life may be rare, but in an infinite multiverse, even rare outcomes must occur somewhere. The cold spot, then, becomes more than a curiosity. It could be the first observational hint that our universe is part of a far larger cosmic structure, a small patch within an eternal, self-replicating expanse. If the multiverse is real, the implications are staggering. Each universe would represent a different outcome of the same underlying physics, with its own version of reality unfolding beyond our horizon. Some might contain forms of matter and energy utterly alien to us. Others might have collapsed back into nothingness moments after forming. Yet all would share a common origin in the inflationary sea that preceded them. And though collisions between universes would be catastrophic for anything within them, their faint after-effects might be the only way we can ever glimpse that greater reality. Even as evidence remains uncertain, the theory serves as a reminder of the scale on which nature operates. The cold spot, whether born of quantum randomness or a cosmic collision, speaks to the same truth. The universe is not a static arena, but a living process of creation, expansion, and transformation. Its anomalies are not flaws, but clues, hints that what we see is part of something vastly larger. From this possibility of colliding worlds, our attention shifts back to the structures within our own, the cosmic web of galaxies and voids, shaped by gravity and dark energy alike. Following these threads draws us closer to understanding how even the smallest fluctuations in the early universe grew into the vast architecture we now see stretching across space and time, echoes from other realities. Across the faint murmur of the cosmos, there are whispers, subtle imprints in the oldest light we can see that some physicists believe might be evidence of realities beyond our own. These are not echoes in the ordinary sense, but possible remnants of interactions between our universe and others that may exist alongside it. If true, they would mean that the cold spot in the cosmic microwave background is more than an odd patch of temperature. It could be the shadow of another cosmos brushing against ours long ago. The idea begins with inflation, that brief, furious expansion in the universe's first instant. During inflation, quantum fluctuations, tiny variations in energy, were stretched to cosmic scales, becoming the seeds of all future structure. But in certain inflationary models, this process never completely ends. Instead, it continues eternally in most regions, spawning countless pocket universes within a larger, inflating space. Each pocket cools and stabilizes independently, forming its own physical laws and constants. This framework, known as eternal inflation, predicts not a single universe, but an infinite ensemble, a multiverse. Within this cosmic ocean, the boundaries between universes behave like expanding bubbles. When two bubbles form close enough, they can collide. The collision is unimaginably violent. Waves of energy ripple through space-time, reshaping the newborn cosmoses on either side. The aftermath of such an event, though smoothed over by time and expansion, could leave permanent scars in the form of large-scale anisotropies, regions of higher or lower temperature in the cosmic microwave background. One such region, some theorists suggest, could be the cold spot. This possibility was explored in 2017 by researchers studying the data from the Planck and WMAP satellites. They noticed that the cold spot's size, symmetry, and coherence did not match ordinary random fluctuations predicted by the standard model of cosmology. It appeared too distinct, too organized. Statistical simulations indicated that while such a feature could arise by chance, the odds were remarkably low, less than 1%. That led to a provocative idea. Perhaps the cold spot is not a coincidence at all, but an ancient signal, a lingering echo of a collision between our universe and another in the distant past. If another universe had a slightly different vacuum energy, the impact zone could imprint a circular distortion on the background radiation. The edges might appear subtly warmer or cooler, depending on the energy differential and how the gravitational fields interacted. Simulations of bubble collisions show temperature patterns that resemble what we observe in the cold spot, a central dip surrounded by a faint ring-like gradient. Though the resemblance is not proof, it remains one of the few scenarios that can produce a feature of such magnitude without invoking chance. But the evidence remains elusive. The difficulty lies in distinguishing true cosmological signals from the statistical noise of an imperfectly observed universe. The cosmic microwave background, for all its precision, is only one realization of the universe's initial conditions. We cannot repeat the experiment. Some alternative explanations, like the Eridanus supervoid, provide a more conservative fit. An enormous, underdense region that cools background photons as they pass through. Yet even that model does not fully account for the cold spot's scale and symmetry. It explains part of the effect, but not the whole. Beyond cosmology, the concept of other universes finds support in quantum theory. In some interpretations, such as the many worlds hypothesis, every quantum event produces branching realities, each realizing a different outcome. These quantum universes are not physically separate in space. but coexist within a larger mathematical framework. The echoes we perceive might, in a broader sense, be the statistical shadows of these parallel branches, though not in any measurable way. Still, the convergence of ideas, quantum multiverses, inflationary bubbles, and cosmological anomalies suggests a deeper unity we do not yet understand. The pursuit of these echoes has become a frontier of modern cosmology. Researchers are developing statistical tools to scan the CMB for non-random circular patterns, the predicted fingerprints of bubble collisions. Others are probing the polarization of microwave light, where such collisions could leave distinctive alignments. Thus far, no definitive detection has emerged, but the search continues, driven by a quiet conviction that something extraordinary might be hidden in the data. Even if the cold spot is ultimately explained by a local void or random fluctuation, the fact that it invites such speculation speaks to the boundless curiosity of science. It shows how even a faint patch of cooler light can open a window onto questions of cosmic origin and structure. If we ever confirm that another universe once touched ours, it would not merely expand our understanding of space, it would redefine existence itself. Our universe would no longer be the singular stage of creation, but one verse in a vast cosmic symphony, each playing its own distinct melody in an eternal chorus of creation. In the faint glow of the microwave background, then, we may be hearing not just the echo of the Big Bang, but the overlapping resonance of many beginnings, each universe leaving its quiet trace upon the next. And as we follow those whispers through the geometry of space-time, we approach the edge of what science can describe, and perhaps the threshold of what reality itself can contain. From the possibility of echoes that cross cosmic boundaries, our attention drifts toward the quieter harmonies of structure within our own universe, the delicate interplay between gravity, matter, and emptiness that continues to shape the vast architecture of the cosmos today. The multiverse whisper. Amid the faint glow of the cosmic microwave background, light older than the first stars, there are patterns so subtle they seem almost imagined, whispers written across the fabric of time. Among them, one anomaly stands apart, a great, cool blemish stretching across the southern sky, known simply as the cold spot. For years, its presence has teased scientists with the possibility that our universe may not be the only one. Perhaps, hidden behind that strange patch of chilled light lies evidence of another cosmos pressing faintly against our own, a quiet echo of the multiverse itself. The story begins in the first moments after the Big Bang, when the infant universe expanded at unimaginable speed in a process known as cosmic inflation. In less than a trillionth of a second, space itself grew exponentially, flattening irregularities and smoothing out the primordial chaos. This expansion wasn't perfectly uniform. Tiny quantum fluctuations, minute differences in energy, were stretched across vast distances, becoming the seeds of galaxies and clusters. But according to the mathematics of inflation, this process didn't occur just once. Inflation could continue indefinitely, creating new universes in a ceaseless chain reaction. Each pocket of space that stopped inflating became its own self-contained cosmos, while the surrounding regions continued to expand, spawning still more universes in an infinite cascade. This idea, called eternal inflation, gives rise to the concept of the multiverse. In this framework, our universe is but one bubble floating in a vast cosmic foam, surrounded by countless others, each with its own laws of physics, its own geometry, perhaps even its own version of time. Some bubbles might contain no matter at all, only dark energy expanding forever. Others could host exotic variations of physics where atoms, stars, and galaxies could never form. And occasionally, two bubbles may form close enough to collide, When that happens, the fabric of space-time ripples with unimaginable energy, producing a shockwave that can alter the physical constants within each universe. Theorists have long speculated that such a collision could leave behind observable evidence. If another universe brushed against ours in its earliest moments, the impact might produce a circular imprint on the cosmic microwave background, a region where the temperature differs ever so slightly from the surrounding sky. The cold spot, with its anomalously low temperature and distinct boundary, matches what some models predict a cosmic collision scar would look like. It is, in essence, the kind of bruise one universe might leave upon another. Attempts to verify this possibility have been cautious but persistent. In 2011, a team at University College London, led by Stephen Feeney, analysed data from NASA's Wilkinson Microwave Anisotropy probe to search for the telltale signatures of bubble collisions. Their statistical models identified several circular patterns that could fit the theoretical predictions, though none rose to the level of proof. Later, the European Space Agency's Planck satellite provided higher resolution data that reaffirmed the cold spot's existence, but left its origin unresolved. The observed temperature difference, about 150 microkelvins below average, was significant enough to defy easy explanation, yet not so extreme as to confirm a cosmic collision outright. Skeptics argue that the cold spot may simply be a statistical fluke, a rare but natural feature of a universe filled with random fluctuations. Others propose that it could be linked to a massive underdensity known as the Eridanus supervoid, an immense region of space with fewer galaxies than average. Light passing through this vast emptiness loses a small amount of energy due to the universe's expansion, creating a subtle cooling effect known as the integrated Sachs-Wolf phenomenon. However, even when the void's contribution is accounted for, it doesn't fully explain the depth of the anomaly. Something more seems to be at work. If the multiverse interpretation is correct, then the cold spot represents far more than a cosmic curiosity. It would be the first physical evidence that our universe is not alone, that beyond our horizon, beyond even the limits of our observable reality, lie endless other worlds governed by their own versions of physics and probability. Such a discovery would fundamentally change cosmology, transforming the universe from a single, self-contained system into one of countless universes within an infinite, ever-expanding structure. Yet, for all its grandeur, the idea of the multiverse remains both alluring and frustrating. It offers explanations for deep questions: why the physical constants of our universe seem perfectly tuned for life, or why the universe appears flat and homogeneous on large scales, but it also challenges the very foundations of empirical science. How can we test what may forever remain beyond our cosmic horizon? The multiverse whispers possibilities, but refuses to shout them aloud. Still, the search continues. Scientists refine their measurements of the cosmic background, study gravitational lensing in the region of the cold spot, and explore new models of inflation that might predict more precise signatures of interuniversal contact. Each data point, each refinement, brings us closer to understanding whether we truly live in isolation or as part of a grand cosmic archipelago, where each universe drifts in a sea of eternal creation. If the cold spot is indeed a message from beyond, then it carries with it a haunting beauty. It suggests that the story of existence may have no true beginning or end, only endless variations on a single theme, repeating across the infinite. As we continue to listen to the universe's faintest murmurs, we may one day learn that what we call everything is merely one note in a chorus that never stops singing. From this notion of universes beyond our own, the path forward leads us back to our cosmic foundations, to the mysterious forces that shape space, time, and energy themselves, and to the quiet patterns that still ripple through the afterglow of creation. Patterns in the infinite. Across the vast expanse of the cosmos, the universe appears uniform at first glance, a grand canvas painted in even strokes of light and matter. Yet beneath that apparent smoothness lies a quiet complexity, a delicate patterning that reveals the fingerprints of creation itself. These patterns, preserved in the cosmic microwave background, are the subtle temperature ripples that formed when the universe was less than 400,000 years old. They are not random noise, but structured variations, tiny fluctuations in density and energy that would one day grow into galaxies, clusters, and superclusters, the scaffolding of all visible matter. The story begins with sound, cosmic sound. In the young universe, matter and radiation were intimately linked in a hot plasma, a fluid of light and particles moving in rhythm. Gravity pulled matter inward, while radiation pushed it back out, creating oscillations across space acoustic waves rippling through the primordial sea. When the universe cooled enough for atoms to form and light to travel freely, those ripples were frozen into the radiation itself. The cosmic microwave background, or CMB, is a record of those frozen waves, a snapshot of the universe's first great symphony. When scientists first mapped the CMB in detail, they found not chaos, but harmony. The temperature variations measured in millionths of a degree followed precise statistical patterns that matched predictions from the theory of inflation. Inflation explains how, in a fraction of a second, quantum fluctuations were stretched across unimaginable distances, imprinting structure into the very geometry of space-time. What began as microscopic randomness became the blueprint for everything. The slight over-densities that would attract more matter, the slight under-densities that would form cosmic voids. From this balance of compression and expansion, the cosmic web emerged. To understand this pattern mathematically, cosmologists study the power spectrum of the CMB, a graph that measures how much structure exists at different scales. Its peaks and troughs are not arbitrary. They correspond to the acoustic vibrations of the early universe. The first peak represents the largest regions that completed a single oscillation before the universe became transparent. The second and third peaks show smaller harmonics, echoing through space like the overtones of a resonating instrument. Remarkably, the relative heights and positions of these peaks reveal fundamental properties of the cosmos, its age, composition, and geometry. Through these measurements, scientists have determined that the universe is about 13.8 billion years old, composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. The patterns in the microwave sky confirm that space is geometrically flat to extraordinary precision, meaning parallel lines would never converge or diverge even across cosmic distances. The CMB, in essence, serves as both the origin story and the ruler of the universe, a single image containing the entire architecture of reality. And yet, even within this near-perfect order, there are irregularities. The largest of them is the cold spot, that puzzling region where the temperature dips lower than expected. While most of the CMB's variations can be explained as the natural outcome of inflation, the cold spot seems unusually large and coherent, suggesting it may be more than a simple statistical quirk. It might be a window into deeper physics, a hint that the underlying fabric of the universe is shaped by something beyond randomness, perhaps even by interactions with other cosmic regions beyond our horizon. Some researchers propose that such anomalies could arise from the geometry of space-time itself. If the universe is infinite but not entirely uniform, its vastness could contain subtle gradients or warps that produce local asymmetries. Others suggest that inflation may not have ended everywhere, in the same way that certain regions could bear the marks of different inflationary histories, creating variations we now interpret as irregularities. These small deviations, though barely measurable, carry profound implications for how we understand the laws that govern the cosmos. The patterns in the CMB also link to a broader tapestry, the cosmic web of galaxies that stretches across billions of light years. Supercomputer simulations of cosmic structure formation begin with the same fluctuations observed in the microwave background, then evolve them under the influence of gravity. Over time, dense regions collapse into filaments and clusters, while vast voids open in between. When the results are compared with galaxy surveys like the Sloan Digital Sky Survey, the match is nearly perfect. The universe, it seems, has been following its original score with astonishing fidelity for nearly 14 billion years. The perfection of these patterns carries a strange kind of poetry. They remind us that even the most chaotic processes can give rise to order, and that the infinite can still hold structure within its boundlessness. Every galaxy, every star, and every atom traces its origin to those tiny ripples in the early light-minute imperfections that made complexity possible. Without them, there would be no stars to shine, no planets to orbit them, and no observers to look back and wonder how it all began. The pattern continues to evolve, its rhythm carried by dark energy into the accelerating expansion of space. As this expansion stretches the cosmic web ever thinner, the echoes of those primordial ripples grow fainter, but they never fade entirely. Tracing their imprint forward leads us toward the great cosmic voids that now dominate the universe. Vast, near-empty regions where gravity weakens and silence deepens, marking the next frontier in the story of structure and symmetry across the infinite. The universe that remembers. Long after the first light faded, the universe began to write its memory into structure. Every cluster of galaxies, every faint wisp of radiation, and every darkened void preserves a trace of what came before. Though it has no consciousness, the cosmos behaves like something that remembers its vastness, shaped by the lingering echoes of ancient forces, frozen patterns that carry the imprint of its earliest moments. This memory begins not with life or intelligence, but with physics itself. When the universe emerged from the Big Bang, it was almost perfectly smooth, an expanding plasma of matter and radiation. But not quite. Tiny quantum fluctuations, born from uncertainty at subatomic scales, were stretched by inflation into vast ripples across the fabric of space. These ripples were the first imprints, the earliest records etched into reality. As the universe cooled and light separated from matter, those variations became visible in the cosmic microwave background, the afterglow of creation. In that faint radiation, we can still read the first page of the universe's history. Over billions of years, gravity amplified those slight differences. Regions a little denser than average pulled in surrounding matter, forming stars and galaxies. Regions a little emptier expanded into the great cosmic voids. What we see today, the cosmic web of filaments and clusters, is the mature form of those original patterns. The shape of the universe is, in essence, a memory of its beginning, encoded in matter and motion. The cold spot itself, that strange patch of the sky where the ancient light runs cool, may represent a particularly deep scar in this memory, a relic of an early fluctuation magnified across billions of light years. Physics gives the universe many ways to remember. Matter and energy interact according to laws that ensure continuity. Momentum, charge, and energy are conserved. Nothing disappears without a trace. When particles collide, the outcomes still carry the imprints of their initial states. Even entropy, The tendency of systems to move toward disorder is a kind of cosmic recollection. It tells time which direction to flow, preserving the sequence of events that brought the present into being. The entire arrow of time, past to future, is the unfolding of that stored information. This principle extends to the largest scales. The cosmic microwave background is not the only archive of memory. Galaxies too record the universe's evolving story. Their rotations reflect how dark matter shaped their growth. Their chemical compositions reveal the generations of stars that lived and died within them, seeding the cosmos with heavier elements. Even the distribution of galaxy clusters across space encodes the subtle tug of dark energy over billions of years. In a very real sense, the universe remembers through the geometry of its own expansion. At the smallest scales, quantum mechanics guards its own peculiar record. According to the laws of quantum theory, information cannot be destroyed, not even by the most extreme processes. When a star collapses into a black hole, the matter that once composed it vanishes from view, yet the information describing it is thought to persist, subtly woven into the fabric of the black hole's event horizon. This idea, known as the black hole information paradox, has led physicists to one of the most profound insights in modern science, that the universe itself might be a kind of hologram. In this view, every three-dimensional process we observe could be encoded on a vast two-dimensional surface, a cosmic memory written across the boundary of space-time. If this is true, then the universe does more than simply evolve. It continually records its own history in the structure of reality. The past is never truly lost. It diffuses into radiation, gravity, and quantum entanglement, leaving behind traces that can be measured, modeled, and understood. Every photon of the cosmic microwave background is a messenger carrying the memory of its birth, and every gravitational wave that ripples through the cosmos tells a story of massive bodies that once moved, collided, or vanished. In a way, memory defines the universe's continuity. Without it, there would be no patterns, no causality, no way for complexity to arise. The persistence of information allows stars to form, life to emerge, and minds to wonder about the past. Even the cold spot, whether born from a supervoid or a collision with another universe, is part of this grand recollection, a reminder that every irregularity has meaning written in its temperature and shape. As cosmologists trace these records deeper into the past, they find that the universe's memory is not a static archive but a living process. The structures we see today are not merely fossils. They are the ongoing result of forces that began at the dawn of time and continue to echo across the infinite. In studying them, we are reading a cosmic diary that was never meant to be forgotten. And as these echoes fade into the background, the next pattern begins to emerge, an even larger rhythm shaped by the unseen influence of dark energy, stretching the universe further apart and writing new lines into its endless, expanding memory. A silent signal from beyond. In the background of all existence, there hums a faint and ancient whisper, a nearly perfect glow that fills every direction of the sky. It is not light from stars or galaxies, but the remnant of the universe's own birth cry, stretched and softened over billions of years into the cold microwave radiation we now call the cosmic microwave background. Within that whisper lies a mystery, a region colder and darker than the rest, a silent signal that seems to come from somewhere beyond our understanding. The cold spot, as astronomers have named it, first appeared in the early 2000s in data from NASA's Wilkinson Microwave Anisotropy probe. At first, it looked like a statistical curiosity, a patch of sky a few degrees across, slightly dimmer and cooler than theory predicted. When the Planck satellite later confirmed it, the anomaly became harder to dismiss. The difference in temperature, only a few hundred microkelvins, was minute but significant enough to raise eyebrows. The universe, as far as we know, should be nearly uniform at this scale, and yet, in this one direction, the ancient light seemed to falter, as if echoing from a place where something vast and strange intervened. One possible explanation is entirely natural. The cold spot might be the result of a supervoid, an immense region of space containing fewer galaxies than average. As light from the early universe travels through this emptiness, it loses a small amount of energy, stretched by the weakening gravitational pull of the sparse matter inside. This effect, known as the integrated Sachs-Wolf phenomenon, could slightly cool the light that reaches us. In 2015, astronomers using data from the Dark Energy Survey and the WISE infrared telescope mapped a region in the constellation Eridanus that matched the cold spot's direction. It appeared to be a cosmic void nearly 2 billion light-years wide, one of the largest known. For a moment, the puzzle seemed solved. But then the numbers refused to agree. Even a void that large could only account for a fraction of the cold spot's depth. The temperature drop was simply too great, too coherent, to be explained by ordinary structure. If the void was not enough, then perhaps something else, something older or stranger, had left its mark on the cosmic background, and so attention turned to the idea that this faint, frozen scar might not belong to our universe alone. According to some versions of inflation theory, the Big Bang was not a singular explosion, but part of a far grander process, a continuous inflationary field giving rise to countless universes, each forming as a bubble within an infinite cosmic foam. If two such universes were to collide in their infancy, the impact could leave an imprint, a circular blemish, on the cosmic microwave background, a kind of bruise where one cosmos brushed against another. The cold spot's shape and symmetry fit the predicted signature surprisingly well. Could it be that we are seeing, in the faintest radiation imaginable, the lingering evidence of another universe pressing against our own? Such a collision would have been catastrophic at the time, but subtle in its aftermath. The edges of our universe's expansion might have slowed or warped where it met the boundary of another, altering the distribution of energy across the primordial plasma. Billions of years later, that disturbance could manifest as the anomaly we now observe. If true, it would mean that our universe carries within it a fossil of an event that happened before time, as we define it, even began a silent message from a cosmic neighbour that no longer exists within reach. Yet, not all physicists are convinced. Some argue that the cold spot could simply be an improbable but natural fluctuation, an extreme outlier in the cosmic statistics. After all, in a universe of infinite possibilities, even the rarest patterns will eventually appear. Others suggest subtler causes, such as variations in dark energy or hidden effects of cosmic topology. Still, the allure of the multiverse hypothesis remains, if only because it provides a framework in which such anomalies make sense. If there are countless universes, each born with different physical laws, then collisions are not just possible, they are inevitable. What makes the cold spot so compelling is its persistence. It has survived every refinement of measurement, every recalibration of data, every attempt to dismiss it as an error. It remains there, quietly defiant, a soft hollow in the texture of the oldest light. Whether it is a void, a statistical oddity, or a relic of something unimaginably vast beyond our cosmic horizon, it is a reminder that the universe still holds secrets too large to fit comfortably within our models. If it truly is a signal from beyond, an echo from another universe, then it would mean that even in the silent background of creation, the boundaries between realities can leave scars. The universe may not be an isolated story, but a single chapter in a larger, eternal narrative of birth, collision, and expansion. From this faint anomaly, the cosmic microwave background continues to glow, smooth and serene, its ripples charting the geometry of all we can know. And yet, at its edge, the cold spot endures an unexplained whisper woven into the oldest light, suggesting that somewhere beyond the reach of our telescopes, another reality may have once touched our own. From that quiet meeting, perhaps, the universe itself still hums the memory of a signal sent long ago, waiting for us to listen closely enough to hear it. Wonder that never ends. There are moments when the universe feels less like a collection of matter and more like a thought, vast, unending, quietly aware of itself through us. The farther we peer into space, the more its calm defies comprehension. What began as a glowing fireball of radiation has unfolded into a cathedral of galaxies, light and gravity arranged with the precision of an eternal clock. Yet, despite centuries of exploration, each revelation seems to deepen the mystery, not resolve it. The cosmos appears to invite understanding, while always keeping part of its truth just beyond reach. In the faint relic light of the cosmic microwave background, we see the first structures of existence, frozen in time, nearly 13.8 billion years ago. It is the universe's oldest photograph, showing the instant when atoms first formed and light could move freely through space. The slight temperature variations across that radiation, mere millionths of a degree, became the seeds from which all structure grew. Galaxies, clusters, and superclusters arose from those delicate differences as gravity sculpted order from chaos. The cold spot, that improbable region of lower temperature, stands as a quiet reminder that the universe is both patterned and imperfect, as though designed to provoke endless curiosity. What science has revealed is astonishing enough. Stars forging elements in their cores, black holes bending space-time, dark matter shaping the unseen skeleton of galaxies. But perhaps the most extraordinary discovery is that the universe itself is still expanding, and not just expanding, but accelerating. This acceleration, driven by something we call dark energy, means that space itself is stretching faster than the pull of gravity can contain. Distant galaxies are not simply moving away. The very fabric between them is growing, carrying them beyond our ability to ever reach or even see them. This realization changes everything. It means that there are regions of the universe already lost to us forever, light that will never arrive, civilizations that could live and die under alien stars, their entire histories hidden beyond the cosmic horizon. The more the universe grows, the smaller our observable portion becomes. One day, even the nearest galaxies will fade into invisibility, leaving only our local cluster adrift in silent darkness. Yet rather than diminishing the universe's grandeur, this knowledge magnifies it. The cosmos is not a closed story, it is an ongoing act of creation, still writing itself across incomprehensible distances. There is, too, something profoundly human about our response to this immensity. Across centuries, from the astronomers of Babylon to the physicists at CERN, we have always sought to measure the infinite, to name the unnameable. Our species, confined to one small planet, has mapped the shape of space-time itself. We have watched stars die, seen galaxies collide, and traced radiation from an age before time had meaning. In doing so, we've discovered that the laws governing the cosmos, the same equations describing electrons, gravity, and light, apply universally. The same physics that guides the flight of a falling apple governs the rotation of entire galaxies. And yet, within that shared structure, lies something profoundly poetic. Every atom in our bodies was once inside a star, fused in the heart of some long-vanished sun. The iron in our blood, the calcium in our bones, the oxygen we breathe, all of it forged in cosmic furnaces billions of years before Earth existed. We are, quite literally, fragments of the universe made conscious, pieces of ancient stars capable of looking back and understanding the processes that created us. Even in its coldest places, like the mysterious region of the microwave background, the universe is never empty. Quantum fluctuations stir within the vacuum, virtual particles appear and vanish, and space-time itself hums with subtle energy. The same mechanisms that shaped the cosmos in its infancy still whisper in its dark corners today. Every void, every silent expanse carries a memory of motion, a faint aftertaste of creation that refuses to fade. There is something enduring about this quiet persistence. The universe does not rush, and it does not end in understanding. Each time we think we've uncovered its final secret, we discover only a deeper layer, particles beneath particles, forces beneath forces, and perhaps even universes beyond our own. Science is not so much a conquest of knowledge as a dialogue with the unknown. Each answer deepens the question, and the wonder only grows stronger. Even the cold spot itself, so small a feature in the endless sky, reminds us that the universe is not perfectly smooth or predictable. Its very strangeness keeps us honest, humbling our assumptions and inviting us to look again, to measure more precisely, to think more deeply. It reminds us that our understanding, though vast, is still a flickering light within an ocean of shadow. And so, the wonder continues not as an end, but as a rhythm woven through everything we learn. Every discovery opens another horizon. Every explanation reveals another layer of mystery. The cosmos is not something to be solved, but something to be witnessed. A story that has no final page, because it is still being written in light, in matter, and in the endless curiosity of the minds that dare to look up and listen. As we follow that curiosity outward, through the stars and beyond the cold relics of time, the same sense of awe draws us onward to where energy gives shape to emptiness, and the silence of space begins to reveal its next secret.